Hello, everyone, and welcome to the fourth session of the Sunoikisys Digital Classics fall semester. This session is the first in two sessions about GIS, Geographic Information Systems. Both sessions will be led by Tom Elliott and Chiara Palladino. And today we will focus on encoding geographic data. So, Tom, please.
Good morning or good afternoon as the sun strikes you. I'm going to take a few minutes here at the beginning of the session to introduce some basic concepts in geographic information systems as they apply to some aspects of humanities computing, and to provide definition of a few terms. And then I'll hand things over to Chiara, who will sort of expand from there and start to talk about some of the data formats that we use and some of the kinds of applications. And then we'll culminate with some demonstrations of a few applications, and that will begin to set the stage for more detailed discussion at the next session. So I'm going to share my screen so we can look at some slides. And we'll see how that goes. And I guess I'll present this so that it maybe looks good. Let's see what happens. Oh, promising, promising. Okay, so here we go. So GIS is a term we toss around quite a bit. It stands for Geographic Information System. And if you want to spend a few hours having a discussion, get a few sort of mid-50s geographers together and have them talk about the history of GIS and what the term means. There actually has been quite a lot of discussion in the field about what is and what is not a geographic information system and how to define them. I don't want to get into that arcane and disciplinary discussion today, but I do think it's worth highlighting the basic fact, which ought to be obvious from the term, that we're talking about computing systems and information structures that are designed to be somehow specifically geographic. In most cases, when people are talking about geographic information systems, they mean specifically managing, analyzing, comparing, changing geographic information that's understood to have coordinates, things that you could map. Geographic information systems are not strictly tools for making maps. Rather, they are information systems for gathering, working with, querying, and visualizing geographic information. The map is one of the most obvious, but not only mechanisms of visualization. So this is the space we're working in. There is a whole subdiscipline of geographic or of computing and geography that is sometimes called geographic information science, and it gets its name from geographic information systems. There have also been reactions to the dominant structures and modalities of geographic information systems that have led people to talk about computing systems and information systems that are lowercase GIS, meaning they wouldn't necessarily be recognized as a GIS practitioner as a GIS, but they are nonetheless computing environments for working with geographic information. In some cases, this is information understood to be geographic. That is to say, it's about place. It's about relationships between places and humans, but not necessarily done in the traditional way with coordinates. There are computing systems for working with these kinds of constructs. There are also people who talk about UNGIS, which is a feature really of the 21st century and web computing practice, and we'll come on to that in a second. And then we have things that we call digital gazetteers, which are principally, though not always, lists of place names with associated geographic information. And here the emphasis is on toponymy and geographic description rather than on coordinates. So it's essentially taking the telescope of the GIS and looking at it from the other end. In GIS, coordinates are the principal organizing component of the information. In a digital gazetteer, it's usually names that are the principal organizing mechanism. But both will have both things in them. It's worth taking a moment to reference the fact that coordinate systems and the modeling of the Earth or another planetary body as a spatial entity that can be described numerically and referenced numerically is a complex matter. It is a matter that has antecedents in practice that go back centuries, well before the beginning of geographic information systems as a computing concern. There is not time today for us to slog through this. In fact, there are whole courses that geographers are put through on coordinate systems, and people who spend their entire professional careers working on such concerns. There's an accessible introduction that I've cited here online that you can use to get a little more information if you're so inclined. But what I want to highlight are two things. Basically, that we can have different kinds of coordinate systems for talking about where something is in space. There are two-dimensional and three-dimensional geographic coordinates. These are the latitudes and longitudes that you hopefully learned about earlier in your academic career. My daughter learned about them first when she was 11 in school. And then we also have sometimes used geocentric coordinates, which place a three-dimensional coordinate system at the Earth's center and then measure things in that three-dimensional space. This is less intuitive than the latitude-longitude approach that many of us are familiar with. And then there's various Cartesian coordinate systems, so X and Y axes, within which the Earth's surface is interpreted or mathematically modified to be represented as if flat in that coordinate system. And then we can talk about elevations within it, but the idea is to get to something that can fit on a paper map, a flat surface, and that you can make some kind of measurements across. The mathematical process for getting from a three-dimensional quasi-spherical world to Cartesian coordinates is generally called a projection, although that term can also be used for going from reality of three-dimensional space to any other of these representations. To make projections work, you have to have reference models for all the things involved, and this is where terms like spheroid and geoid will be commonly heard. These are complex, sometimes, mathematical models for the real shape of things. The Earth is not a perfect sphere, therefore we call it a spheroid. The Earth does not have a uniform gravitational field that is symmetrical in all respects. On and on and on. There are numbers of concerns that you have to address when you decide how accurate you can possibly be in recording, referencing, and then transforming coordinates from one system to another. One of the key things that GIS does for us is it manages these kinds of computing tasks. The math has been worked out by the people I referenced earlier who spend their careers working on coordinate systems and reference models. And the geographic information system is programmed to be able to recognize data that conforms to one or another of the common conventions, and then to perform the necessary mathematical transformations to project that information from one coordinate system to another. Why do you need to do this? Well, because information comes in a number of systems. Whether it's taking data from a map or from a census record or something else, it will make use of one of these coordinate systems and reference models, but you may have data that has to be brought from multiple coordinate systems and reference models into a common one so that you can compare, contrast, and analyze. I'll briefly touch on the history and development of GIS and GIS formats, which I hope will set us up a little bit for what Kara is going to talk about. Geographic information systems as a computing concern begins in the 1960s, proceeds through the mid-1970s. This is a period dominated in large part, although not completely, by work in North America and in the UK, in which large government programs undertook to create computational systems for dealing with some particular aspect of governance. So the recording and analysis of land ownership. A key one in Canada was an assessment of land use. How is the land being used? What is the relationship of that use to economic concerns, to taxation concerns, and so on. And census is another major area where these early geographic computing approaches came about. One of the important early techniques that was used in building these systems was the application of thematic layers, which is to say that the data was not just all piled into a computer system, but was organized the same way you would organize a conventional map-making production. Maps in the 20th century were generally made by creating layers of information on clear mylar or plastic or other kinds of materials. And then these layers would be built up. So you would start with, for example, a layer that described the contour surfaces of the Earth. So this would be inked onto something, and then a clear layer would be put on top of it that inscribed the coastline, another layer for the major drainages and rivers, another layer for lakes, and then you'd add cultural features and so on. So you'd have this layer cake, and that's the metaphor that's often used for these, that builds up the map that then is photographically transferred to paper. That way of looking at the world, of dividing up the information into thematic groupings and then layering them one on top of each other for display, was the model adopted by early geographic information systems. And the earliest systems made use of that layer in a very literal way. It was a graphic layer, a two-dimensional Cartesian coordinate system in which there were cells of information, each of which could have a color value or a darkness value or some other value of interest. And so these kinds of gridded data sets were created, and then mathematical constructs were computed for calculating across the layers. So you could, a very simple one is to or and in a logical way a set of these, so that in the first cell, if neither cell was lit, then the resulting cell would be also empty. Whereas if one or the other of them were lit, your resulting layer set would be lit. And this, these kinds of computations could be used to figure out to compare soils and various other things based on the information that was provided. But there were also developments in what we call vector GIS formats, even during this period. And these describe spatial entities with respect to their location and sometimes direction or magnitude, and can be used to actually mathematically describe features like a line or a curve or a polygonal feature. And these are very commonly used in all sorts of GIS applications, and in some ways provide more flexibility than the raster approach. And if there's a computer involved, you can't get away from tabular data formats. This is all the extra stuff that's not explicitly spatial. They're sometimes called attribute data in GIS. And this will be the name you want to apply to a feature, maybe a label you want to put on it, some other kind of information that's not represented in the pure geometrical form. As the 1970s gave way into the 80s and 90s, we saw a shift away from these bespoke governmental computer systems to the development of generalized software systems and data formats that could be used in the computers of the day. Mainframes moving into micro and mini computers, then moving into desktop computing. And that's the real revolution in GIS that brings it out of major government programs and into individual offices, whether it's at your local administrative level, whether it's at an academic institution or whatever. It's that 20-year period from the 70s or 25-year period through the mid-90s in which GIS takes advantage of the developments that are occurring in generalized computing and generalized software to come to the desktop, and to do it in a way that provides the basic mechanisms for creating geographic information sets and doing calculations, rather than something that's specifically designed for Canadian land use or that's specifically designed for the US Census. We get generalized systems running on the desktop. Of course, the World Wide Web brings change when it comes in the 90s, and so we start to see attempts to figure out, well, what should be happening on the desktop versus what should be happening on the web, and this happens across software, and of course it happens in GIS. We have the introduction of new paradigms that break out of this kind of layer cake Cartesian model, digital globes like Google Earth and NASA's Whirlwind being some examples. And we have different data formats that are in some ways more suitable to use on the web. Things that don't take this idea of thematically grouping stuff into tables, but rather treat each feature, each geographic object, each place as a distinct data record, and doing it in a way that facilitates models that we see more often in social networking, for example, graph models. So there's that whole big change in just the last 20 years that happens. And that sets us up then to talk about historical and archaeological GIS utilization, which develops alongside these concerns. From early days, we start to have interest in things that are not something you would go out and survey right this minute, but things that are past in some way. One major activity, especially of the 90s and early 2000s, was historical maps and georeferencing. So we have lots of maps that predate GIS, and they have, if we're historians, things of interest on them that we'd like to get into the GIS so we can do more computational work with them. And so techniques were developed for the scanning and the realignment of map information in order to move us from whatever mathematical projection was used for that particular map to the one we want to use in the GIS because of our other data. The term of art for some of that work is georeferencing. It's also sometimes called rubber sheeting, in which the digital scan of the map is treated like a flexible sheet that can be stretched and pulled to match it up with another coordinate system. There's also interest in boundary studies that develop, the attempts to identify either from historical maps or by other computational means ancient boundaries, historical boundaries. Whether these boundaries were things that were surveyed in contemporary culture or were de facto by virtue of some visible change in linguistic or archaeological practice or other things. There are approaches for doing this. Other historical data can have spatial aspects. We can find plenty of textual material, other kinds of records, physical information that has some spatial aspect. And we like to get this into the GIS too, so that we can compare it, contrast it, and total it. Remote sensing, both from aircraft, ranging from balloons and airplanes to drones, as well as satellite and rocket-borne mechanisms, give us new ways of finding things on the Earth's surface. Not only things that are recently built, but the remnants of ancient things. And so that whole raft of data that comes from flying things above the Earth's surface and looking down at it in various wavelengths with various kinds of electromagnetic radiation gives us insight sometimes into past practice. An early example of this was work that Tom Seaver did on the Anasazi Road system in the American Southwest, which was one of the first applications of remote sensing for historical geography. Viewshed analysis is a commonly used technique for exploring the relationship between places and topography. So this takes known or projected locations of historical or archaeological interest and examines the surrounding landscape to assess what can be seen or could have been seen from these particular locations. So someone has, yeah, thank you, Monica. We also, in GIS, undertake various kinds of tasks in an attempt to predict things. So we look at the analysis of settlement patterns in archaeology and apply the rules and approaches that we see a particular people using to construct known settlements and apply them to a landscape that hasn't been surveyed in an effort to predict areas that might have been particularly attractive or particularly successful for a people to construct cultural sites. Field recording with GIS is another area where archaeologists make use of it. Basically, as you're moving around a survey area or a site, you are moving in space, and what you find in particular places, the spatial aspect of that finding is clearly of analytical interest for the archaeological enterprise. And so you want to capture it in spatial terms, and this can be done directly into the GIS, provided that you can bring to bear the necessary technology on site. I'll just close this portion of the session by mentioning again our friends, the Gazetteers, who take an approach that's a little bit different from GIS, and that can help GIS, specifically by sorting out all the different names for things and getting them associated with the coordinates. Gazetteers also have another definition in computing practice that we ought to pay attention to, which is in the arena of natural language processing. A gazetteer in natural language processing is not necessarily a spatial thing, but is a list of terms or proper nouns or other things that you want to be able to capture in a text that's being computationally analyzed. And so spatial gazetteers that are digital are of value in that particular area of natural language processing that we refer to as geoparsing, which I think may have been touched on a bit last week. So that's our high-speed tour through the history and basic concepts of geographic information systems. And what I'd like to do now is stop sharing my screen and turn the virtual podium over to Chiara, who's going to take us to the next level with data representation and such.
Okay, thanks. So we'll share my screen as well so that everybody can see. Okay. You should be able to see now.
Yes, yes.
Okay, perfect. So we will start presenting. So I will very briefly cover the topic of the different data formats that you can have while you're looking for spatial information in primary sources, essentially, because that's the focus of my research. And I will show you some possibilities in terms of geoencoding or encoding of spatial information that comes from primary sources, basically, essentially textual sources. So we mentioned briefly the opportunity that comes from geoparsed entities, geoparsed spatial data that is essentially data that come from several types of natural language processing that are applied to primary sources or secondary sources, namely atlases and dictionaries and so on, in order to get, let's say, a primary list of information and of types of names that can be essentially connected to spatial information and coordinates. There are several other ways to retrieve some kind of spatial information from a text or from a document. And I will just very briefly introduce one of the options, which obviously is markup. So you can characterize and you can obviously store spatial information of various kinds, also semantically distinguishing several types of spatial information through different markup languages. Of course, one option would be applying a markup language directly to your document. Since in this particular round of Sunoikis, probably the basic information about markup hasn't been explained yet, I will just very, very briefly introduce what we mean by markup language. Basically, a markup language is the equivalent in a machine-readable format of a print text. A print text doesn't just have the text in it, but it has some particular markers, some particular experience in the way it is visualized by the human eye that make the information that is in it semantically different, semantically distinguished. And this is what a markup language does. A markup language gives you a set of markers to allow a machine to recognize some specific functionality to some of the features in a text. And one of the technical characteristics of a markup language is obviously that it has a set of rules, which is called the validating schema, that is associated with the markers in a given context that will basically give you a set of options that you can use in order to encode your text in a markup language of your choice. And it sometimes also has a vocabulary, which is a set of markers that are specifically employed with a semantic function. And of course, one of the most popular markup languages would be the XML, that is frequently used in order to make machine readable any kind of text, basically. For text, we particularly use the TEI, which is a text encoding initiative, that is an inline markup language that has been conceived in order to have several options of encoding for basically any type of information. It is language that was made up in order to be particularly flexible. What is particularly relevant for us is how you can mark through inline markup several types of spatial information with TI. I will go very briefly with this because I would like to share other more GIS-related data formats, but this is, let's call it the basics. This is the easiest and at the same time the most complicated way with which you can encode spatial information in a text. It is the easiest because it's the easiest to learn. It is the most complicated because it's manual, it's entirely manual, and you will need to come up with a specific routine of encoding in order to mark all the information that is relevant for you and for your particular source, because again, TI is a particularly flexible type of markup language. So there is a specific unit that you can use in order to encode the so-called named entities. Here we are essentially interested in places. So there are 3 essential types of tags that you can use to encode information that is related to place names. One would be obviously the place name tag, the geographical name, which is associated to physical geography entities, and the geographical feature, which indicates the feature name. And of course, there will be various examples of how to use those particular types of tags. With TI, you can also create your own little gazetteers. We mentioned this before with Tom, and I would assume that since last session, many of you will know what we mean with authority lists and gazetteers. You can have your own internal authority lists with TI if you have the particular need to have a specific gazetteer or a specific authority for your file, or of course you can relate on your on the several resources in terms of external gazetteers that you can have. There are also more complex ways of encoding spatial information in TI. One would be the location, which is essentially the way to encode geographical coordinates that are associated with place, or another set of options, which would be the offset tag that allows you to mark the relative spatial dimension that is indicated regarding a place, which would be that typical vaguely indicated spatial location that is very frequent in texts, like locations indicated in terms of proximity, near to, next to, behind, without any specific indication of their coordinates. And then, of course, there would be the tag geo, which is normally used to mark coordinates in a standard system. So I will skip the relation option because I would go with some applications. One of the most immediate applications that you can have with the XML option is to create an index of places, which can then be used in order to retrieve information from gazetteers, in order to go directly to the text from where you have retrieved the information, and so on. So there you go. Another markup system that I would like to briefly introduce here is another example of inline marking system for complex relational information of space, which is the markdown that has been introduced here in Leipzig by my colleague Maxim Romanov. And it was originally meant to be used just for Arabic sources. And it is particularly easy to use, although it looks monstrous from this particular slide, but it is basically made up as a set of tags for geographical relations. So you can encode particular types of geographical relations, such as the administrative divisions or the indication of a direction or the indication of a distance, with a set of tags that are provided by the markdown system. This would be an option like the geographical tagging of routes and distances. The difference between the TI option and the markdown option is that markdown option gives you the option of encoding spatial relations. So the entities that you annotate with markdown are related as far as you use the proper geographical tagging. And this means that the visual representations that are allowed with markdown, once you extract the information and you associate them with coordinates, are a bit more complex and a bit more elaborate than what you would have with traditional markup systems. Not only with maps, of course, but you can see here one of the options for the visual representation of administrative divisions. You would see the preliminary, the bigger administrative division at the first level, and then you would see all the different levels of administrative divisions in the several branches of the graph. Another option which you probably went through in the last session is the option of annotation. To a set of coordinates that are provided by an external reference or an external authority. And this is why this type of annotation is called external or standoff annotation, because it's not directly stored in the file that you are using, in the file that you are annotating, but it refers
Chiara,
to an external reference. Yes?
We do not see your screen anymore.
Can you see my screen?
No.
No. Okay. Let's see what's going on. Okay. Can you see it now?
No.
Okay, we'll stop sharing and see if
Yes.
something went wrong.
Maybe you can sign out and rejoin.
Yeah. I will rejoin.
Out quickly, yes.
Okay. I will share the screen again and see what happens. Okay, you should be able to see it now.
Yes, we see it now.
Okay, perfect. So again, we were speaking of the annotation and saying that an external annotation has an external reference basically to a gazetteer. And this is probably what you have seen with Recogito, which is essentially a tool for place annotation and association with gazetteer references and so coordinates. I will go then briefly into the geodata formats possibility. There are several options for encoding and storing geospatial information that is automatically retrieved from a text. And it essentially depends on how you want to store that type of information and what type of information you have to do with. One of the most popular and flexible formats for encoding various types of geographical features is GeoJSON, which is a variant of the JSON language. And when I think about the GeoJSON option is that it gives you the possibility of encoding different types of geographic features. And it is extremely flexible, as I said. You can pretty much decide to store any kind of information that is related to your particular database. And one of the options that I like most is the option of encoding the different types of geometry, which is essentially the idea that a place is not necessarily a point that is identified with a certain set of coordinates, but it can be also a polygon, so an extension. And if you encode that in GeoJSON, there are good chances that you can also visualize it relatively easy on a mapping tool. Another of the very traditional markup languages that are used specifically in order to encode geographical information is the KML language, which is a keyhole markup language. That is, again, a derivative of the XML language, which we talked briefly about before. And as you can see here, this is a small example. It uses the same kind of formal requirements of XML, and you can store your information in terms of KML, provided that you add this little thing here, which would be the namespace. And KML is one format that was originally introduced, and it is, I think, still used for Google Earth. So if you want to represent your own document in Google Earth, which is a relatively straightforward thing, you can have your information stored in a KML format. And of course, as we mentioned, the rawest type of tabular data that you will have out there is a CSV type, so comma-separated values, which is essentially any kind of text file that stores any kind of data with maximum flexibility in a tabular format. If you open it in an application like Excel, for example, it will have the shape of a table, but its original format is essentially, it's very, very easy to actually, and it consists of a series of values that are separated by a kind of punctuation. It can be a comma, but it can also be semicolons or another kind of field separator. So I think that we should definitely go to the topic of the visualization. And I will probably pass this topic to Tom so that we just get into the topic of usage of geospatial tools, and then we can get a bit more into the theoretics of geospatial visualization and mapping afterwards if we have time. But we really wanted to show you something practical, so we'll just leave the word to Tom.
Yeah, thanks, Kara. I think what I'd like to do first is to demonstrate one particular example of getting information that you have aligned with with geographic data so that you can begin to work within another environment. And then we'll see if we have time to talk about visualization. If not, we'll carry that on to next week. At any rate, so I'm going to share my screen here, and we'll talk about this. So foreground on the screen, and I'm going to make it bigger, is a text file containing a few place names. And let's say that these are place names I've come across in reading something that I want to be able to associate with space. There are a number of, depending on what I'm reading, what discipline I'm in, there are any number of resources that a person can go to try to find this out. Since these are ancient Roman names, I'm going to first want to turn to Pleiades, which I think was introduced last week, to try to find out just where these places are. And if I'm a human and I have a few, the easy way to do that is with the front page search, and then I can go to the appropriate place page, see the information I want, and if I wanted to collect the coordinates, I could do that right there, or I could go look at the content in one of the other linked applications, in this case Google Earth, which would give me a modern view of the area where Pleiades says this ancient site, Dertona, was. So we can see the nice roofs of an Italian town. But if I am a researcher or a museum curator or an archivist who regularly needs to be able to find out the locations of things and then use them in other kinds of mapping or analysis applications, the idea of one by one looking up a place in some external resource like Pleiades is pretty daunting and ultimately prohibitive in terms of difficulty. So just in terms of, you know, the sheer tedium of doing it over and over and over again. So what we want to look for are other tools that can be used to make the process faster. Chiara's alluded to some of those, the process of geoparsing attempts to do those kinds of things. But let's look at something more simple. Let's look at a list that I've created of places. Let's imagine that it's a lot longer so as to justify the business of taking a computational approach here. Pleiades provides a relatively recently developed service called GeoCollider that can help when you have a list of place names that you want to find in Pleiades. It's easy enough to find by Googling for Pleiades GeoCollider and following the first link. There's a little bit of a blurb that explains it. We're going to ignore that because we just want to get on with things and go straight to the website. GeoCollider takes a tabular data file in the comma-separated value format, CSV, and gives you a way to load it into Pleiades and have it try to match up with the content that's already there. So I'm going to take my little list here and turn it into a CSV file, which is pretty easy to do. I'm going to give this column of information a name, and I'm also going to create my own project identifier, which is just a number. That right there is a comma-separated value file. We have some values, and they're separated by commas, hence the name, comma-separated value. And we have a first line that's a header. I'm going to save this file as a text file on my desktop. And I'm going to end it with the .csv file name extension so I can remember what it is. Then back to GeoCollider. I'm going to click Choose File and navigate to that CSV file and open it, and then choose the Upload button. GeoCollider and other tools that know how to work with CSV in this sort of way will do something similar. The first thing it's going to do is it's going to look at the data file and try to make sure it understands what I've given it. It gives me a preview. That's a check to make sure I haven't uploaded something other than CSV. And then it says it thinks it sees two columns of data by interpreting the comma as a delimiter, and it lays out for me the first few rows. I'm then given the option of tweaking its interpretation. Chiara alluded to the fact that you can use something other than commas. You can use tabs. My first row contains column headers. That is the case, so I've made that indication. If I had columns that contained latitude and longitude, I could supply these to GeoCollider, and it would use that information to help narrow the possible choices for the place names that I'm entering. But the important thing is I need to indicate what my identifiers are. That's the ID column. And then the columns that contain names. In this case, that's really easy. I called it names. And I have a choice of how the matching process will occur. I could do it based only on latitude and longitude. That would be place-only matching. I could do it based only on the names, or I could do it based on a combination. Since I'm not providing any latitudes or longitudes, I want name only. And then I have some options for how closely the character strings of the names will be matched. I could have it do it literally, but I want it to ignore white space differences. I don't care about capitalization. If I had accents or punctuation in my names, I might be concerned with that. I might also, if I'm dealing with a script other than the Roman script used for English, I might want to make some changes there based on Unicode encoding, but I'm not going to worry about it. I can also constrain how far away a matched place can be in terms of kilometers. I'm going to leave it set to this fairly broad 8-kilometer number. I'm going to click Process. Sometimes GeoCollider is very fast. Sometimes it's slower because of the on-demand computing platform that it's running on. I have also taken the risk of changing some of the settings I used when I tested this a few minutes ago, so we may get a result that's unexpected. And the result is another CSV file that is downloaded to my downloads folder. Here it is. I'm going to open it with LibreOffice, which does a good job reading CSV files and is open source. And it's doing the same thing that GeoCollider did, which is looking at the results and saying, have I understood your file correctly? Blah, blah, blah. I'm going to say, yes, you have, and we'll see what sort of fancy results we got. Well, we got a number of matches corresponding to the identifiers I used in my list. You'll recall that number 1 is Dertona, and it thinks there's only one possible match for Dertona. We'll go see if it got it right. In our judgment, that's Dertona. So we are very happy with GeoCollider. It's got its act together. But then we might be surprised by the fact that there are 3 possible matches for our second name, which was Iria. And so we would want to go check those and work out what is the difference between these entries. There is a settlement named Iria. The second one is a river called Iria. And the third one is another river called Iria. So here we see both the value and limitations of this kind of approach. We can get a homonymous matches if we're only working on place names. But we've also got a first pass on making our list of places match up. So this is a basic tour of GeoCollider, and it introduces a concept that is often called gazetteer alignment, in which you have a collection of names, possibly also coordinates, that you want to align or collate with a gazetteer, with the result that then you get the identified information back. Sometimes you have to do post-processing, or what we sometimes euphemistically call human supervision. You have to exercise over the computational result in order to make sure you've got exactly what you want, and then you can go on and do things. Well, what would you do with this? Well, if this was information that was associated, let's say, with objects in an exhibition, and I'm in the process of trying to make a map to go in the exhibition catalog, I could then take the Pleiades IDs, use them to get the Pleiades coordinates, which can also be done computationally, and then produce my map in another mapping tool. I can also get involved with the Pelagius network, which was discussed last week, and could be aligning the information in my collection with Pleiades so that my collections webpage or web application can participate in the Pelagius network. So there's a lot of things you can do there. And getting past how do I get coordinates is your first step. How do I match stuff up? If you've got that sort of information, you're then looking for mapping tools. And I want to introduce one that is closely tied to the Pleiades community, and that's Antiquity a la carte, which is a web application produced by the Ancient World Mapping Center at the University of North Carolina. You can find it by searching the web for Antiquity a la carte, or by going to the web page for the Ancient World Mapping Center and looking for it there. But you can also get to it from Pleiades, which I'm going to use as a shortcut. Under any Pleiades place map, there are a series of links that can take you to other applications. In this case, I want to look at Dertona in Antiquity a la carte. This loads the Antiquity a la carte interface and begins to draw its background. Antiquity a la carte right now is in version 1, and it's running on a server that is a little bit slow. There's work in progress to move it to a faster server, and in fact to refine the way the web application works to make it faster overall. But I can tell you the first hint I always give people to Antiquity a la carte if you want to watch the map draw faster is to turn off the hillshade and elevation data layers. This gets rid of some big rasters that have to be pulled from the Ancient World Mapping Center server, and then you can zoom and redraw more quickly. Here's Dertona, and we have a map that we can zoom around in. It's going to redraw the watercourses if we let it. What's good about Antiquity a la carte? Well, it lets you do some things that Pleiades doesn't let you do, which is to make a custom map. I can use the interactive map gazetteer to manipulate the contents of my map. I can use the search for features function to add things to my map. I can add material coming from Pleiades. Let's say we want to get Rome onto this map. There's Rome. I'm going to add it to the map. Now I have Rome and Dertona, and so you can start to build up a custom map that it's then possible to export. You can export that map as data, so comma-separated value, JSON, or KML, the formats that Chiara was introducing earlier. If you export it as KML, you'll be able to look at it in Google Earth. If you export it as JSON, you're ready for any number of web mapping applications. And then CSV is sort of the universal can opener of export data formats. And so you can go to, whether you want to go to Microsoft Excel or you want to go to a database or something else, CSV is a great way to go. There's also mechanisms for printing your map and for generating a URL, a web link, that you can embed in a syllabus or in a web page that will allow the user to come back to this same view that you've created later. There are mechanisms for changing how the map is labeled. Some instructors like very much to only put numbers on and then direct their students to the map or make them print it out and make the students label the numbers correctly so as to prove that they've learned where the geography lies, and a number of other mechanisms for interacting with and customizing the map, including printing the thing to a printer or to PDF for use in a publication context. The Antiquity a la carte, which was largely produced by Ryan Horn, who is now at the World Historical Geography Center at the University of Pittsburgh. This whole system was designed specifically to meet sort of basic pedagogical and publication mapping needs of scholars of the classical Mediterranean. And consequently, it's got all of the Pleiades data available in it. You can also use the file upload function to add data in the GeoJSON format that you got from another source, customize your map, and save it for whatever purposes you need to. And there's no limitations on the reuse of those maps other than citing, what tool you use to create it. So that's a basic introduction or overview, if you will, of Antiquity a la carte, which is just one of the many mapping tools that are out there on the web. It's one that's specifically designed for practitioners of ancient studies to make use of. And so I thought it was particularly appropriate to look at today. But perhaps now, with the time we have left, Chiara, do you want to gloss a little bit some of the things you were thinking about in terms of additional use cases, or is that stuff we should defer to next week?
As you want, actually. I would like to know if there are any questions, first of all, so that we can cover that part. And if you're interested, I can show you something in terms of more advanced computational stuff.
Yeah, so let's open the floor to questions.
Okay, so thank you, Chiara and Tom. Does anybody have questions or comments? I'm going to look on the YouTube as well to see. Mm-hmm.
I have a question, if I may. For the both of you, it's just something I'm curious about. So the first person that doesn't answer, it's okay. So Tom, you mentioned the process of let's say stretching ancient maps, historical maps, on top of modern geocoordinates, and I've seen that done with some historical maps of Italy, and I thought that was, quite a brilliant job. I really enjoyed that. I thought it was really useful. So my questions are: is that still something that is done, and do you both think that the community is actually interested in having such resources? Like, it could be interesting, for example, to involve people in crowdsourcing these kind of processes. And the other question is, on average, are they actually reliable, or the stretching becomes, the adaptation becomes so more, it weights more than the accuracy in the end, in your opinion?
I have a few thoughts about it. So the more modern a map is, in terms of the cartographic and survey practices that were used to create it, the more satisfying the results of georeferencing and rubber sheeting are. So things that are 19th and 20th century that made use of triangulated survey can be, if they were done right, very good. And there were very good people building those kinds of maps. And so there's been quite a lot of work done, both at the regional scale and with sort of city planning and early cadastral survey, that's really quite good. The further back you go in time, you're also tending to go down this path of less spatial accuracy in terms of the way the stuff is captured and so on. Particularly once you pass the space where we have reliable chronometers for judging exactly what time it is, and therefore what your longitude is. You will see biases start to skip in, and then around about that change, you can still see coastlines that are very good, but once you go inland, stuff breaks down. So, you know, if you're on a ship and you've got a sextant and you can do a good job of doing your astral referencing, you can still get a good map of anything you can see from there. But and then the further back you go, when you get things that are not really conforming to a mathematical projection, people who either don't know their Ptolemy or don't want to, then it really becomes pretty crazy. We did some experiments with little pieces of the Poitinger map, which is this presumably late Roman map that survives in a medieval copy that's in the National Library in Vienna. And it has other cartographic rhetoric going on. Certainly, you know, the people who made it must have known their Ptolemy, but for whatever reason, they weren't using it for this particular application. They know the shape of the land, but they subordinate it to the format, this long strip map that they've got. And the way the work we did on that proceeded was not by using this rubber sheeting method, but rather to identify the places with their modern equivalents, or you know, by means of Pleiades and Barrington Atlas and other things, to get modern coordinates corresponding to those places. So we did not try to first rubber sheet the thing into GIS. And that'll be true of other kinds of maps and cartographs as well. The other thing you have to watch out for is scale of the map. So even if you were to register a Barrington Atlas map in GIS, what you would find based on the scale of the map is that the dots, the little tiny dots on the map, are some kilometers in diameter on the Earth's surface by virtue of the scale relationship between the map and reality. Consequently, it means that any point you might have clicked in your GIS to say, ah, yeah, that's the center of that dot, could actually be anywhere in that 2 or 3 kilometer bubble. And so this is actually the source of certain discontinuities you'll still see in Pleiades, where what we have is the raw digitized point from the Barrington, and you're comparing it, let's say, with Google Earth, where you have a much higher resolution by virtue of the satellite imagery there, or aerial imagery they're using. So those are some of the factors that can be involved in that. And I've talked a lot longer than I intended to.
It was interesting, thank you.
You were mentioning crowdsourcing efforts, and I think that there was a project, I think it was Old Maps Online, that had this kind of idea of georeferencing old maps against, you know, a very, very modern cartographic conventional map. And of course, you can also georeference your own map with QGIS, which is relatively easy. And of course, that has a pedagogical value because students learn that maps are not necessarily based on cartographic conventions. And this is particularly true for pre-modern maps, or any sort of thing that was designed, apart from Ptolemy, not for essentially navigational purposes or mathematical purposes as well. But of course, it really depends on what is your purpose, what is your goal in doing that type of thing.
Yeah, thank you both. I asked because that is one of my favorite things that you can do with digital maps, and I was surprised that, you know, not everyone is doing that. So I was wondering, you know, if it was, you know, way more problematic than it seemed. Yeah, thank you.
It all depends. It all depends.
Okay, does anybody else have comments or questions for the speakers?
I don't have a question, but I see that in your class outline you have an exercise. I don't know if it is your plan to talk about that, but maybe given that we have students also using our material, maybe we can mention something about the exercise. I see that I'm reading that, so, and students can use, of course, their data on, or you mentioned 2 possible data sets. I don't know if you want to say something about that.
Yeah, there was actually an old exercise that we kind of improvise. So there are two data sets that are provided there, and if I recall correctly, one is the database of the Roman amphitheaters that was compiled by Sebastian Heath, which is basically a CSV format file that has not only names, locations, coordinates of all the Roman amphitheaters, but it has also several other types of information, like the chronology of each amphitheater, the emperor under which it was built, and so on. And there is also a KML format file, which is the Mapping Spartacus file. That is a project that was developed in the Pleiades Sarah Bond that has a more pedagogical scope, I would say. And the exercise, as we originally thought, was to incorporate these different categories of geographical data into a mapping tool. We mentioned a couple of those, which would be QGIS and Carto, Google My Maps. If you're more practical with programming languages, you can also use Leaflet if you want, or OpenStreetMap as well. But also Antiquity a la carte would be a very good tool to use where to ingest these types of data. I would recommend QGIS to Windows users because it tends to be a bit of a pain to install and to run on Mac. But you can do that, of course. Carto is an online tool that is not particularly straightforward to use. It needs a bit of practice, but it's not something that students cannot be practical with. And again, there are more advanced tools like Leaflet that require a bit of practice in terms of programming, especially JavaScript, that can be done only if you actually know your stuff. And different categories of geographical data means essentially try to categorize what you see. As I mentioned, these files that we have here have several types of information that is stored. It's not just about the place name, but it's about trying to understand certain types of historical patterns into the chronology, for example, like asking yourselves why under a certain emperor, amphitheaters were built only in a certain geographical area of the empire, for example. So it's more about asking yourself what you want to see and asking yourself some certain types of research questions that you want to answer. And you can do that, of course, with your own data, which would be particularly easy if you used Recogito in the last session. You would already have your own little data set.
Yeah, Chiara, thank you. This is what I wanted to add to your explanation of the exercise for the people that attended last class, or in general for people that want to have a go at Recogito. They can produce a CSV with geographical data from Recogito, so they can perform their annotations and then just download it as CSV from the download page. For this exercise, I recommend to use documents that only have place annotations. If you had fun annotating people as well, want to delete these annotations because they would be so just leave in the CSV only the place references. You can any of the tools that Chiara and Tom presented, or just Google My Maps, which is very, very straightforward. And, you can just CSV visualizations.
Okay. If this is this all? Does anybody else have questions or remarks on today's presentation? If not, we have the second GIS session next week, so you can keep the best questions for that one. Well, thank you very much once again to the speakers for this great session, and see you both and see you all next week. Bye.
Bye, everybody.